Hello, everyone. So we're going to do a quick example here to walk through the proof that regular expressions are a complete description of all regular languages or all problems that could be solved by the finite automata that we've been studying up until this point. In order to do that, we would need to show the proof in two directions. So we're trying to show that a regular expression describes a language if and only if there is some discrete finite automata that solves that particular problem. Now, to prove this in both directions, we're going to have to say, okay, this should be mutually convertible. We need to show that for any discrete finite automata, there is a regular expression that describes the language recognized by that finite automata. We also need to show that for any regular expression, there is some discrete finite automata that recognizes it. Now, the lower arrow is more straightforward because we already knew from the previous theorems that regular expressions are merely expressions built up of the regular operators, and so we know that any regular expression can be recognized by a discrete finite automata. The upper arrow showing that any problem solvable or recognizable by a discrete finite automata can be recognized by or can be explained and expressed as a regular expression is the subject of today's video. So what we're going to do is show that for any discrete finite automata, and I'm going to leave out the details here. We want to show that there is some regular expression that describes the state, that describes the languages that are accepted by this discrete finite automata. In order to do that, we're going to introduce a new concept which we call a generalized discrete finite automata, where the edges that you're allowed to use are not just zeros and ones, but are arbitrary regular expressions. They're not just in this case, the example is zeros and ones, assuming that's our alphabet, but assuming instead of having our edges only be the characters of the alphabet for our finite automata, we are going to allow any regular expression to be represented on one of these edges. And we're going to specifically use a additional criteria that our generalized discrete finite automata is only allowed to have one start state and one accept state. So we're going to do that by starting to take our normal discrete finite automata, and we're going to convert it into a general discrete finite automata with those constraints that there is one start state and there is one accept state by basically saying, well, these accept states over here, anything that was an accept state before, we're just going to create a new global accept state and say that any accept state that we had before gets an empty string free edge to go to the accept state of our new design. And similarly, anything that could be reachable by a start state is going to have a empty string getting to it from our general start state over here. So now we say this is the beginning of our general discrete finite automata. Now what we are going to try to do is to shrink this general discrete finite automata to the point where we've got one start state, one accept state, and one edge with some regular expression on it. If we can reduce this bigger general discrete finite automata to this one and prove that at each step along the way, the language that is being recognized is identical to the one that was recognized by our original, then this ending point, clearly the language that is recognized by this generalized discrete finite automata is the language described by this regular expression. So this regular expression is an exact descriptor of the language recognized by this finite state machine, which means that it must have also been a description of the language recognized by the original finite state machine. And so the question is, how do we get from here to there? And the way that we're going to do this is by construction, where we are going to provide a recursive algorithm that can take any generalized discrete finite automata with one accept state and one start state and some number of other states and reduces it to a general discrete finite automata with one less state. And the way that we're going to do that is just pick a state arbitrarily and delete it from the graph as a starting point. In the textbook, they call this QRIP. The state that we are arbitrarily choosing to remove from the graph. Now, obviously, we've got some problems here because now we've got a bunch of dangling edges and we need to make sure that however we fix up whatever is left, that the fixed up version of this finite state machine recognizes exactly the same languages that the original one did. And when we say that it recognizes any of these languages, the nice thing about this right now is there's only one accept state and one start state. So we're going to have any path through this graph start with the start state and go to the accept state with some number of states in between here. Now, what we need to show is that we are going to fix this in such a way that if QRIP was ever in a path from a start state to accept state before, then however we have fixed the graph, the same input will still get you from the start state to the accept state. And so we need to consider a few different cases. One case is, well, supposing that we had QI and QJ, where before we were in this state, we took some input to get to this state that we are removing, and then some other input that gets us to a following state, a subsequent state. Well, what we're going to do is say in these two, let's say that this was one regular expression and that was some other regular expression. In this case, let's say that this was our RIP state and we're going to consider this state I and this state J for the time being. In this case, one possible path that you could have taken, well, these regular expressions to get from I to the state that we ripped out means that we would have accepted we would have read an input of 1, and to get from the RIP state to state J, we're going to read another input of 1. What that means then is for this particular path, we could recreate a path for this exact same input by replacing this edge with an edge that combines or concatenates those two inputs to say, let's say we read 1 1, and that replaces the path that would have gotten us from QI to QJ with one visit over to QRIP in the process. So that's a concatenation part, but it doesn't fix all of the other possible scenarios. So the other possible scenarios are maybe we had one instance of QRIP between QI and QJ. Another possibility is that we had multiple instances of QRIP in a row before in between QI and QJ. So in this situation, effectively what we're saying is we've got this other loop edge that was on QRIP that we were taking. And in that situation, we need to take into account the fact that if we had several of these in a row, we need to account for not only the edges that get us into and out of the QRIP state, but all of the input that we might have consumed in the middle. Okay, in order for that to work, we therefore need to say that, well, another possibility in this situation is that we had an input that got us into the state, and we had some number of repetitions of the input that would have allowed us to loop in that state. And finally, we would have been able to get us out of that state, or out of that state into whatever was the next state not equal to QRIP in this path. Which means that the entire expression in this case, if we're removing all of these, needs to account for 3 components. The expression that gets us into the state, some number of instances of the expression that could loop us in that state or repeat that state, and then another expression that would get us out of the state that we removed and into whatever the next state happens to be. So this is what we need to do in order to replace the path and have a direct path from QI to QJ if there were some number of copies of that path for in between the two, in order to make sure that an equivalent input that would have gotten us through a path from the start to QI, which was the state before we got into QRIP, some number of copies of QRIP, then state J, and eventually the accept state at the end. In order to replace that section of the path, but have an equivalent input still reach the accept state, we need to provide a new edge that represents the entire input that would have gotten us from QI to QJ through that ripped out state. Now there's one problem with that. If we go back and fix all of this up, in this case, for I and j that I've labeled here, we can add in that edge for 1, 0, star, 1, and everything is fine. Now, we need to do that for every possible state or pair of states for things that could have gotten into the RIP state and things that could have gotten us out. Well, in this case, the RIP state only ever got us out into state J, but we had another state over here that also got us into the RIP state, and so we need to now consider that for another possible example of state I and state J, the state before the RIP state and the state afterwards. So in this case, we'd go back and say, okay, great, again, we have our new state I, we have our new state J, we'd have some number of copies of the RIP state in between them. And then we would say, okay, what got us in? It was a 1 again. What looped us? It was always a 0. What gets us out? It is still a 1. So it's the same example that we had before. And so what we can do is we can replace this whole thing with a new edge, similarly to what we had before, of 1, 0, star 1. Except there's a problem, because now we essentially have two states with two different edges between them. We have one edge where we can go from I to j taking a 1, and we have another edge that could take us from I to j using 1, 0, star 1. And that's not allowed in this generalized discrete finite automata. We still are only allowed to have one edge between any pairs of states, unlike the non-deterministic finite automata that we had seen earlier. And so what that means is that now we need to provide this as an alternative. We need to fuse these two edges into one by saying that this edge is labeled with the union, because union is a regular operator. We are going to say you can get across this edge either by accepting an input of 1, 0, star 1, which we generated from replacing the ripped state, or by taking an input of 1, which was just the simple edge that we had there originally. So using this process, we have now defined a correct generalized discrete finite automata with one less state than what we had before. And by fixing up the edges as we designed in this algorithm, we can say for certain that any input that would have gotten us from start to accept in the original graph will get us from start to accept in the new graph, because if any of the path didn't ever include the rip state, it is unmodified. And if a path did get us through the ripped out state, well, we have introduced this new edge, or either introduced a new edge or modified an existing edge to have an additional way to go directly from state I to state J by accepting the input that would have gotten you from state I to state J by traversing through the ripped out state. And if you apply this process enough, you will get down to a generalized discrete finite automata that only has two states, our start state and our accept state, and a regular expression connecting them by a single edge. And that proves by construction that any discrete finite automata can be converted into a regular expression that recognizes exactly the same language. Therefore, the two are equivalent. Regular expressions can describe every problem that is solvable by a discrete finite automata. So I hope that helped, and if you have any questions, please let me know.